Hello everyone. In this video, we will be discussing about principal plane and principal stresses, and even we will be discussing about the stress tensors. So first, we'll discuss about the principal stress. We know that in general stress systems, the equations for normal and shear stress on an inclined plane is given by tau theta is equal to sigma x plus sigma y by 2 plus sigma y minus sigma x by 2 into cos 2 theta plus tau sine 2 theta, which we already discussed in the previous derivations. Just have a look on that one, how we got this one. Now, this can be further simplified as tau theta is equal to sigma x minus sigma y by 2 sine 2 theta plus tau cos 2 theta. Here, the normal stress is maximum on the plane which is inclined at an angle theta, and it is given by tan 2 theta is equal to 2 tau divided by sigma y minus sigma x. The plane on which the normal stress is maximum and the shear stresses are absent is known as the principal plane, and the corresponding normal stress usually we call it as the principal stress. In general, at any point in a strained material, there are three principal planes mutually perpendicular to each other. Out of the three planes, the plane which carries the maximum normal stress we call that as the major principal plane, and the corresponding stress we call it as the major principal stress. So, the plane carrying minimum normal stress is called the minor principal plane, and the corresponding stress is the minor principal stress. So, in two-dimensional analysis, only two principal planes exist. Let us consider one equation which I will be showing in the coming slide, which actually represents the inclination of the principal plane. This can be represented with a right angle triangle with an angle 2 theta. Here you can able to see that. Let me consider a two-dimensional plane where the sigma x, the shear stress is acting on that one. So you can able to see the sigma x here, here, and even sigma y here and here, and this is the principal planes where I have shown here, because these two planes will be having more stress. So these planes we are calling it as the major plane, principal planes, and the stress which is present on these two planes we call as the principal stresses. And here you can able to see this is a right angle triangle with an angle 2 theta, where this is we will be writing as sigma y minus sigma x, and here stress will be the double of the times. So shear stress, so it is 2 tau, and this will be like square root of sigma y minus sigma x whole square plus 4 r square. So from the triangle and from the trigonometry, we know that sine 2 theta is equal to plus or minus 2 tau divided by square root of sigma y minus sigma x whole square plus 4 tau square. So this we know that this form I have written by using the sine theta, which is nothing but opposite by the hypotenuse. So here you can able to see the load has been distributed equally in the all four planes, but only at two planes, since it is a 2D, only at two planes the maximum stress is present. That maximum plane only we are called as the major principal planes. So, and even the in terms of the cos, if you want to write means, which is adjacent by the hypotenuse, so I will be writing it as sigma y minus sigma x divided by square root of sigma y minus sigma x whole square plus 4 tau square. By substituting these equations, the previous equations, we will be getting sigma n, that is a normal stress, equal to sigma x plus sigma y by 2 plus or minus sigma y minus sigma x by 2 into sigma y minus sigma x divided by sigma y minus sigma x whole square plus 4 tau square. This 3.4 equation I am substituting here, and next I will be substituting 3.1 equation. So 4 tau square divided by square root of sigma y minus sigma x whole square plus 4 tau square. By simplifying these equation, finally I will be getting sigma n is equal to sigma x plus sigma y by 2 plus or minus 1 by 2 square root of sigma y minus sigma x whole square plus 4 tau square. So the principal stresses can be written as for the plane 1 and plane 2 as sigma n1 is equal to sigma x plus sigma y by 2 plus 1 by 2 square root of sigma y minus sigma x whole square plus 4 tau square, and for the plane 2 is sigma n2, which is equal to sigma x plus sigma y by 2 minus 1 by 2 square root of sigma y minus sigma x whole square plus 4 tau square. So these two stresses we call it as the principal stresses, that is which is present under the principal plane. So now we'll move to the next important topic, that is the stress tensor. So let me start the topic with the stress tensor equation, where I'll be denoting it as sigma ij is equal to sigma 11 sigma 12 sigma 13. In second row sigma 21 sigma 22 sigma 23, and third row sigma 31 sigma 32 and sigma 33. The first subscript keeps track of the plane, the component which is described by its unit normal vector, while the second subscript keeps track of the direction. So each component represents a magnitude for that particular plane and direction. Here the cuboid only I have taken for the example, where you can able to see that what is sigma 11, what is sigma 22, what is sigma 23, all those things clearly you can able to see that. And even in the sketch 2, there are four 9 components of the stress tensor acting on a normal cubic fluid element. So the stress tensor is always symmetric. So whenever we are substituting the values, where we can able to say that the first row vectors, the first row values will be always equal to the first column. Similarly, the second row and the second column. So that is why here I will be writing sigma ij is equal to sigma ji. Thus, there are only 6 independent components of the stress tensor. So, stress tensor calculus will not be required in this particular course. So, here I will be showing some examples. First, let me say it for the simple shear, where sigma 12 is equal to sigma 21, which I can able to write as the sigma, that is normal stress, which is equal to load by area. And similarly, when I go with sigma 13, which is equal to sigma 31, and sigma 32, which is equal to sigma 32, if it is equal to 0, means if I substitute these terms in the previous equation, I will be getting sigma ij is equal to, only in the principal diagonal, I will be getting sigma 11, sigma 22 and sigma 33. Remaining, and here I will be getting sigma. Remaining places it becomes 0. And here you can able to see that the first row and the first column values, it is symmetrical. Now, and a simple extension, if I go with it, means where sigma ij I will be getting only in the principal diagonal, I will be getting sigma 11, sigma 22 and sigma 3. In remaining locations I am getting it as 0. And for the hydrostatic pressure, it is sigma ij equal to, in all the the principal diagonal, we will be getting only the load value in the negative direction. So this negative sign indicates the pressure goes under compression. So minus sign indicates the compression. So the polymers in the most of the fluids are nearly incompressible. For an incompressible fluid, the hydrostatic pressure does not affect any properties. For this reason only, the differences in normal stresses are important. In simple shear, the first and the second normal stress differences are, we can write it as N1 is equal to sigma 11 minus sigma 22, and N2 is equal to sigma 22 minus sigma 33. The extra stress tensor is defined as, here I have defined, that is shear of ij is equal to sigma ij plus p for I is equal to j. When I is not equal to j, it is only sigma ij. So this completes the stress tensor with the examples. If you have any doubts, post your comments in the comment section.